Have you guys eaten today?
Yeah.
Have you guys breathed today?
Yes. Yeah.
Have you moved today?
Yeah.
While these questions may seem obvious and even ridiculous to ask, all of these actions are a result of chemical processes taking place in your body all day long. Through chemical kinetics, we understand that the rate at which a chemical reaction proceeds is equivalent to the change in concentration of reactants consumed by the reaction over time, or the change in concentration of products formed by the reaction over time. The rate measures how quickly reactants are converted into products. Many chemical reactions' rates only depend on changes in reactant concentration, so this differential equation showing that the rate of reaction concentration with respect to time is proportional to the concentration of that reactant raised to an experimentally derived power can be used. If reactions in our body like respiration, digestion, and protein synthesis were allowed to proceed without a catalyst, the rate of reaction would be far too slow to sustain life. And well... Luckily, enzymes catalyze our body's reactions, reducing the amount of energy required for the reaction to proceed, allowing it to go faster. Chemical substrates bind to an enzyme's active site, forming an enzyme-substrate complex, before a conformational change occurs and the product is formed, which can then be released so the enzyme can bind a new substrate. Here's a more realistic example where a hexokinase enzyme catalyzes the phosphorylation or addition of a phosphate group to a glucose molecule. Notice how the enzyme does not undergo any permanent chemical change. In 1913, Maud Menton and Leonard Michaelis created the Michaelis-Menten equation. The first equation on screen shows that as an enzyme binds to a substrate, it creates a complex and then a product is released. Each reaction is denoted with K and a number. Michaelis and Menton used this initial equation and performed several mathematical transformations to create an equation that describes how the rate of enzyme-catalyzed reactions changes depending on the concentration of the substrate that's available. This provides a mathematical model that measures enzyme kinetics, particularly how efficient an enzyme is in converting a substrate into a product. In my written project, I'll be analyzing this model, how it was derived, and applying it to some experimental data, some of which has been collected by a world-renowned chemist. Thank you for listening to my presentation.